Think about any journey you've ever taken. A car trip, bike ride, heck, even just walking across a room. How do we actually describe that motion? Not just, where you started and where you ended, but what's happening at every single little instant. Well, that's the puzzle we're going to solve today.
Okay, so let's start with something we all just get. You drive 100 miles, it takes you 2 hours, your average speed is 50 miles per hour. Easy. It's the simple summary of the whole trip. If someone asks how the drive was, you'd probably say, not bad. We averaged about 50. But that 50 miles per hour average, it kind of hides the real story, doesn't it? I mean, it doesn't tell you about the 20 minutes you were stuck in traffic, just crawling along at 10 miles an hour, or that one moment you hit an open stretch of highway and pushed it to 70. To see that level of detail, to know our speed at one specific moment, we need a much sharper tool. So right here, this is the key difference. Average speed, that's the summary of the whole trip. Instantaneous speed, though, that's what your speedometer is showing you right now. But how does a speedometer even do that? How can you possibly calculate the speed of a single frozen instant in time? Well, let's picture this. Imagine a graph of your position over time. To get the average speed, we can just pick 2 points, say the start and the end of your trip, and draw a straight line between them. The slope of that line, the rise over the run, that is your average speed. But an average over 2 hours is way too broad. Let's get more precise. Let's bring those 2 points on the graph closer together. Instead of 2 hours apart, what if we looked at the average speed over just 1 minute? Or, hey, even better, over 1 second. You see what we're doing here? We're zooming in, getting closer and closer and closer to a single instant. And here is where the magic happens. As those 2 points get so ridiculously close that they practically merge into one, the line connecting them totally changes. It's no longer cutting through the curve, it's just kissing the edge at that single point. That line is called a tangent line. And the slope of that line, well, that's our instantaneous speed. And that beautiful idea has a name, the derivative. It's the absolute powerhouse of calculus that lets us find the rate of change at any single instant. Honestly, whenever you see the word derivative, just think slope at a single point. It's really that simple.
This gives us this incredibly powerful framework for understanding motion. If you know an object's position, you can take its derivative to find its velocity. And if you know its velocity, you can take the derivative again to find its acceleration. Position to velocity to acceleration. That's kind of the core mantra here.
And this is where it all starts to feel really intuitive. We can just look at a position graph and instantly read the story of its speed. See a really steep section? That means the object is moving fast. See where the curve totally flattens out? Well, its position isn't changing, so it must be stopped. The slope tells the whole story. And you know what? This logic just keeps on going. We can apply the exact same idea to a graph of velocity over time. So what does the slope of this graph tell us? It tells us the rate at which velocity itself is changing. And what do we call a change in velocity? That's right, acceleration. So this is the first huge takeaway. The derivative, or just the slope, it's like a magnifying glass. It lets us see the rate of change at any single point in time, whether that's position changing to become velocity or velocity changing to become acceleration. Okay, so this all leads to a pretty natural question, right? We've just used this tool to break motion down into smaller and smaller pieces. But what if we want to do the opposite? What if we have the velocity and want to figure out the total distance we traveled? How do we build the story back up? The answer is the other giant pillar of calculus, integration. If differentiation is all about finding the slope at one point, integration is about adding up all of those tiny little changes over a period of time to find the total. It's the process of accumulation, of putting it all back together. And visually, integration has its own simple, beautiful trick. If you have a velocity time graph, the total distance you've gone is simply the area under that curve. I mean, think about it. What you're really doing is adding up all those tiny, instantaneous speeds over the entire time period to get the whole journey. So this is our complete toolkit. They're just two sides of the same coin. To go from position to velocity, you differentiate, you find the slope. To go from velocity back to position, you integrate, you find the area. It's this elegant, perfect symmetry. Okay, theory is great and all, but let's put it all together with a real-world example that every single one of us has experienced, just throwing a ball up into the air. The absolute instant a ball leaves your hand, it's under the control of gravity. And gravity provides this constant downward acceleration of about 9.8 meters per second squared. This fact that the acceleration is constant is the key to the whole story.
So let's trace its journey, right? You throw it up with a big positive velocity. As it rises, gravity is pulling down, so its velocity gets smaller and smaller. Then, at the very peak of its flight, for just a split second, its velocity is 0. And then, of course, it starts falling, and its velocity becomes negative, getting faster and faster on the way down. So how on earth do we graph this whole complex journey of changing velocity? Well, because the acceleration from gravity is constant and negative, the velocity graph is just a straight line with a constant negative slope. That's it. This one simple line tells the entire story of the ball's flight. And just look at how everything we've talked about comes together on this one graph. The slope of this line, that is the constant acceleration of gravity. The area of this triangle up here, that's the total distance the ball traveled on its way up. The exact point where the line crosses the axis, that's the moment it hit its peak, where its velocity was 0. And the area down here is how far it fell. It's all right there.
So the really crucial thing to take away here is that these tools, derivatives and integrals, slopes and areas, they're so much more than just abstract math. They are the actual language the universe uses to describe itself in motion, from a car on the highway all the way to a planet in orbit.
It really makes you wonder, doesn't it? The world is just full of things that are constantly changing, from the flow of money in an economy to the growth of a population. If we can graph them, then calculus gives us the language to read their hidden stories. The only question is, what story will you try to read next?